After kinematics, we always move to dynamics. So guess what? We are talking about rotational dynamics today. And then we will talk about torque and rotational inertia. So for rotational dynamics, it is pen. Okay. We know already from the last lesson when we talked about the torque that the angular acceleration is proportional to the torque, the net torque, tau, that is applied to it. We usually write down not just tau by itself, but we write down the sigma. Sigma means sum of the torques, so sum of tau. It's the net torque. Well, this is kind of similar to the Newton's second law, which said that acceleration, linear acceleration, is proportional to the sum of the forces, right? We remember sum of the forces equals ma. Well, speaking of which, since sum of the forces equals ma, we can say that the acceleration equals sum of the forces over m. And since there is a similarity between the linear case and rotational case, we should expect that alpha is going to be somehow connected to this. We already said it's proportional. But then what plays the role of the mass in rotational dynamics? Well, let's take a look at the simple case when we have a simple body, single particle of mass m moving around the circle. Okay, moving around the center point C, fixed point C. So the radius, the distance from point C to our little particle is r, and then the force applied is this force F. So we know that the torque has to be equal r times F. If we use the Newton's law that says sum of F equals ma, and we remember that the tangential acceleration equals r times alpha from our previous lessons, then we can plug this tangential acceleration into a, because we see that the force is tangential, right? So the acceleration has to be also tangential. Therefore, we have F equals ma equals m and then r alpha. Hey, look at that. Now we can plug that back into our equation for the torque. So tau now is going to be equal r times F, which is this guy times r. So r times mr alpha. And that is going to be simplified to tau equals m r squared alpha. Ta-da! That's going to be our equation number 11. And we have this new quantity mr squared that we call a moment of inertia. I'm going to write it down here. Moment of inertia. And that is for, remember, for one single particle. If we have many single particles, then instead of saying mr, we would have to say sum of mr squared, sum of mr squared. So for sum of t, sigma tau will be sigma mr squared, which means that inertia I, we will label it with letter I, is going to be sum of mr squared m1 r1 squared plus m2 r2 squared plus m3 r3 squared, Helena squared, not 2, okay? And then so on. So many particles. All right, so if you plug that back into our equation 11, then what we get here is we get the sum of sum sigma tau, so sum of the torque, so net torque is going to be equal I, right? I is the sum of those times alpha. So that is another equation that I am going to say it is equation 14. This was equation number 13. I did not label equation 12. It was similar to this one. I'm going to put it right here on the side for us. That would be when we had several particles. So then the net torque is going to be sigma mr squared times alpha. So that's going to be my equation 12. Okay, that goes like that. All right, so what we can see that here is that it's, well, first of all, this is the rotational equivalent to the Newton's second law. And what we notice is that it is, I don't like this I, I'm going to fix the I. It is valid for a rotation of a rigid object around some axis, fixed axis. And because inertia depends on the mass and the radius, if you look at those two cases, if you have the same mass of those two objects, you can see that the large diameter cylinder will have a greater rotational inertia because the radius is going to be greater. And this one will have a smaller. So if we assume that they have the same mass, then what that means is that it's going to be harder to start this one rolling, so we'll have to push it harder, but then it will take longer to stop. So once we got it rolling, then it will keep on rolling longer than this one. Sometimes it can be good, sometimes it can be not so good. So, but that's the fact. All right. Obviously, last thing that we're going to do, no, not last thing. Next thing that we're going to do is we're going to look at this example where we have two weights on the bar. They are 5 kilograms and 4 kilograms. They're 4 meters apart from each other on the diagram. And we are going to calculate the moment of inertia of this system A when the axis of rotation is right in the middle. And for system B, when the axis of rotation is half a meter to the left of the 5 kilograms mass. So here's what we will need to do. We're calculating, so we need to calculate the moment of inertia. Yeah, sum of mr squared. Well, there are only two masses here, and the radius in this case is going to be 2, right? From 4 is the distance between them, so the radius has to be 2. So we are going to multiply 5.0 kilograms times 2 meters, and we have to square it, mr squared, plus 7.0 kilograms times 2.0 meters squared. Forgot to put 0.0. Let's multiply those. So 2 squared is 4. 4 times 5, that's going to be 20 kilograms times meter squared. 7 times 4, that is 28 kilogram. Oh my gosh, no calculator. Wow. And that is going to be equal 48 kilogram times meter squared. So that is our case A. Now in case B, we are using the same logic, but now the distances, the radius is going to be 0.5. So now we're multiplying our 5 kilograms times 0.5 meters squared, and then our 7 kilograms are going to be multiplied times, well, look at this, the distance between the weights is 4 plus another half, so that's going to be 4.5 meters quantity squared. Okay, for this one we can use a calculator. I'm going to multiply them like this: 1.3 kilograms times meters squared plus, and this one is going to give us actually 142 kilograms times meters squared. So we are getting approximately, well, 143 kilogram meter squared, thinking about significant figures. So in this example, we can see that, first of all, the moment of inertia of a system is different for different axes of rotation. 48, 143. Also, we saw that the mass that is close to the axis of rotation contributes very little to the total moment of inertia. Look at this. We only had 1.3 versus 142. So this one is actually less than 1% of the total. So those are the two important points here. And then final thing that I wanted to show you is this graph, this, well, chart, not graph, chart, with different, let me see if I can zoom out a little bit. Okay, so that you have the whole thing on the screen. So in this chart, you have the moments of inertia for different objects, because remember, since if the object is solid, right, the mass, we cannot just say that, oh, all the mass is on the outside of the object, like what we just saw with the diagram. So it depends on how the mass is distributed, which means that if you have a thin hoop with the radius r, that is going to be the most trivial case. That's what we just got, mr squared, the moment of inertia. And it rotates through the center. Well, now when our objects change a little bit, now we have radius r, thin hoop radius r, width is going to be w. So now we have 1/2 mr squared plus 1/12 mw squared. And then if you look at the rest of those equations, they have all those weird sums and weird coefficients, like 1/12. Where does that come from? Well, that comes from calculus. So once we start doing integrals, which is kind of similar to the sums, so we had a sum over here, we simplified it a lot. So sum in integral calculus, or in sorry, in calculus based physics, you will have the integrals, and that's why you will have those very unusual coefficients. But for us, for now, we're just going to accept it as a given, and then we can use that chart in the future. So that is all I had for us for today. I hope you enjoyed the video, and I will see you in class, or not see you in class if you're just watching my videos online. Bye.